Hi, everyone. So my name is Thierry from Power Systems Lab at ETH Zurich. And I would like to present you a piece of work that has been done with Sandro Renggli and Gabriela. So the title is Probabilistic State Forecasting and Optimal Voltage Control in Distribution Grids Under Uncertainty. So uncertainty is probably the most important word in this title. So as you know, there is quite high uncertainty in distribution grids and especially low voltage grids, which comes from consumers, from distributed energy resources, PV systems, and so on. At the same time, we have more and more data which is gathered in distribution grids, mainly from smart meters, which allows to get some insight into the actual state of the grid. And therefore, more and more data-based approaches are developed, for instance, state estimation, control schemes, and so on. But the thing is that most of them are deterministic, even if we have a high uncertainty, or if they take a bit this uncertainty into account, they assume a predefined error distribution, like a Gaussian distribution, which is not realistic in distribution grids. So the first objective of this paper is to develop a so-called probabilistic state forecasting, so kind of state estimation, but in a probabilistic way. And we don't only focus on load forecasting, which is usually done with probabilistic forecasting, but we really want to forecast the whole state. And the second objective is to actually use this probabilistic state forecasts in an optimal control scheme. So here is the outline. So first, this probabilistic state forecasting that we use in an optimal voltage control scheme. We will show case study and finally conclude. So we want to consider two quantile algorithms concerning the state forecasting. So before talking about the algorithm themselves, a few words about the setup. So the idea is to perform hour-ahead prediction of different quantities in the grid, like active and reactive power consumption, voltages, power flows, and so on. And we built only one machine learning model per grid component, so line or bus, per quantity and per quantile. And the core function in these algorithms is the pinball loss. So the idea is that during the training, an overestimation of the error will be penalized differently than an underestimation, and this actually depends on the quantile that we consider. You can see here how the quantile function looks like for different quantile. And when we talk, for instance, about the quantile neural network, I won't go into the detail of the algorithm itself, but the main idea is that the forecast is a combination of input features, and during the training process, we actually want to minimize this pinball loss. Second algorithm that we want to propose and that we have developed for the purpose of this paper is the quantile KNearest neighbor. So it's a bit different than with the neural network. So the idea is that let's assume that we are at time step t, and we want to forecast a certain quantity like the voltage in time step t+1. So we know what is the state at the current time step. And we actually look at similar states in the past, from which we also know what is the target value, like the voltage, if we're interested in the voltage. And then the forecast is just a linear combination of these target values related to the similar states that we have found in the past. When you talk about deterministic forecast, we want to minimize the cost function, which is the difference, the mean absolute error between the weighted target values and the actual value that we're interested in. When you go to quantile forecasting, the mean absolute error is just replaced by the pinball loss. So here is the equation. Then, assuming we know now what is the state in a probabilistic way for the next hour, we want to use it in an optimal voltage control via, in this case, active power PV curtailment. So the idea is to avoid over voltages, and we use active power for that and not reactive power, because we have seen that the forecast of active power is much more accurate than the forecast of reactive power. Of course, reactive power control would be more cost efficient. And we'll present or compare three different approaches. The first one is the real-time optimization strategy that we use as a benchmark. The principle is simple. So let's assume we are in real time and we detect number voltage. Then we run an optimization, which looks like that. The idea is to minimize the cost of active power PV curtailment in real time. And this is subject to different constraints. So we have a limit on the active power curtailment that cannot be higher than the actual PV production. The traditional active and reactive power node balance. Active and reactive power flow equations. We have a limit on the voltage magnitude. And finally, we set the voltage at the slack bus. Of course, we can have other constraints like limits on line flows and so on. Second approach is a two-stage optimization strategy where we use point forecasts, also called 50% quantile. So now we are hour ahead and we assume that we can actually predict what's going to happen in the next hour. And if we predict an overvoltage, then we run an optimization, very similar equations. And in this case, we want to minimize the cost of active power curtailment hour ahead. And we assume that this is going to be cheaper than if we do it in real time. And we have the same kind of constraints at the exception that we don't have measurements of the power and voltage quantities, but here we work with forecasts. Then second stage, we are in real time, and if we still detect over voltages, because the first stage works with forecasts which are not perfect, then we run again the same real-time optimization as we have seen before. And last one, instead of point forecast, we want to use now quantile forecasts. Similarly, we are hour ahead, and if we predict an overvoltage in a certain quantile, here we have some freedom in the choice of the quantile, then we run the optimization strategy, which looks very similarly. But first, let's define what is the uncertainty in the voltage forecast, for instance, which is basically just the difference between the forecast in a certain quantile minus the point forecast. We want again to minimize the cost of active power curtailment hour ahead at a lower cost than in real time, subject to the same kind of constraints. And in this case, since we want to avoid over voltages, we will add this uncertainty to the limit on the voltage magnitude. And similarly with the voltage magnitude at the slack bus. Again, if we detect an overvoltage in real time, we run this optimization in real time. Let's see a case study now. And this is based on a real grid in the city of Basel with about 200 buses, almost 600 residential consumers with 15-minute resolution. So we have actual data, smart meter data. And we simulate the case with 60% penetration of PV systems and 30% of households which have an electric vehicle to give a quite high stress on the grid. Now, a few assumptions we take. So the uncertainty is just on the side of the state of the grid, power injection, power voltages, and so on. But we perfectly know what is the grid topology and the parameters. The loads and the PV systems are voltage independent, and the feeder voltage is maintained after the optimization. So for the probabilistic state forecasting, we do the training on 42 weeks, and we test it on 10 weeks. And this is actually the forecast that we have on 10 weeks that we will use also for the optimization. Here are now the results concerning first the probabilistic state forecasting. So this is an example with the active power flow over 3 days at a certain line. You can see what is the prediction target and also the uncertainty bound around the prediction. First day is highly influenced by PV injection, for instance. We do it with the neural network and with the KNN, and we can see here, for instance, that the KNN leads to much narrower uncertainty bound. At the end, when we evaluate the performance over all buses and over the entire test period, we see that the neural network outperforms the KNN. In this case, we evaluated based on the skill score, and we have considered 4 different penetration levels of PV injections. But in all cases, the neural network outperforms the KNN. Similarly, the voltage magnitude at a certain bus, we did it with the neural network and with the KNN. And in this case, it's quite interesting to see that in the second day, we have exactly this situation where, depending on the quantile that we consider, we will detect or not an overvoltage. When we evaluate now the voltage magnitude based on the skill score, we see that the KNN in this case outperforms the neural network. Now, what about the cost of the optimal voltage control? So as a summary, we have different control strategies. The first one is just real-time power curtailment, and the 3 other ones, we decide an amount of curtailment hour ahead, either using point forecast or quantile forecast. In this case, we consider 2 cases, 44% quantile and 62.5 quantile. And if we still detect an overvoltage in real time, we run the real-time power curtailment strategy. And we consider 2 situations. The first one is when we do curtailment hour ahead, it has a cost of 40 euros per megawatt hour, which corresponds more or less to the average Swiss spot market price. And when we do curtailment in real time, we have this imbalance cost of 63.8 euros per megawatt hour. In the second situation, we just assume that the imbalance price is twice higher than in the first case. And here are the results concerning the amount of energy curtailed and the total cost. So in the benchmark, we only have real-time curtailment. This has a certain cost, which is twice higher in the second situation. For the case with the point forecast, we do most of the curtailment hour ahead, but since we don't have perfect forecast, we need to do a bit more in real time because we still have some constraint violations. So the voltage is still higher than the permitted value. At the end, we have a bit more curtailment, but this still leads to much lower costs in the first situation, but even more in the second situation, because most of the curtailment is done at a cheaper price, or is decided at a cheaper price. And the first situation with the quantile, so we have the 44%, which leads to a bit less curtailment hour ahead, a bit more in real time, but at the end we still have less total power curtailment. And this actually allows to lower a bit the cost in the first situation. And last one, quite conservative strategy where we do more and maybe too much curtailment hour ahead, which leads to higher curtailment than the point forecast case, but it can still lower the cost in the second situation where curtailment in real time is very expensive. So to summarize, the main goal is to encourage the use of quantile forecasts in the optimal control scheme. We have seen different algorithms, one which is good for power quantities, one good for voltages, but actually we can use any kind of forecasting algorithms that is appropriate for this case study. And when we want to do optimal voltage control, it makes sense to do this kind of preventive active power curtailment, which allows for cost savings. And we have seen that depending on the situation, the use of quantile forecast can be more effective than point forecasts. Of course, it would be interesting to look at the voltage control, but based on reactive power control, which would be more cost efficient, and also consider under voltages. And more generally, this kind of scheme can be applied also to congestion management, demand response, and so on. So thanks for your attention.
Thank you very much. Thierry. Now it's time to answer to the questions that you can access.
Yeah, right. So as I can see, I have
if you can read
a few questions. So first one, what is the difference between state forecasting and load forecasting plus power flow calculation? So basically state forecasting, so forecasting of a state. So state is quite general. In this case, so when we talk about forecasting in power system, it's usually about the power or wind forecast or something like that. But here I want to forecast any kind of quantity in the grid, so the power injection, but also the voltages, power flows, and so on. So this is different from just load forecasting because I really use the forecasting algorithm with with a target which corresponds to the voltage or which corresponds to the quantity of interest. So but without forecasting plus power flow calculation, we just do forecasting on the load and then we run the power flow calculation. So in this case we wouldn't have a direct forecasting of voltages, for instance. Second question, can you comment on current industry standards for voltage control? So do they do heuristics, so rule-based, real-time optimization, or predictive control? So as far as I know, current industry standards are quite basic, so mainly rule-based. So and so that they definitely don't do predictive control, as far as I know. Then, third question, since neural network and KNN are not convex functions, how can you guarantee that your solutions converge to the optimum? So I tell that they don't necessarily converge to optimal, so this is a suboptimal solution. That's the issue with the issue that what happens with the algorithms like that, like neural network and KNN. But still, I assume that the solution is accurate enough to to use it in a voltage control scheme, for instance.
Can you just answer to the question of Patrick?
Yeah.
I suggest to stop there because I have to go to the next presentation and to stop on time to not be in conflict with next sessions.
Yeah, all right. I will quickly read the question first. So I understand that there is no temporal dimension in your control. The time steps are computed independently. Could you confirm? Yes, I confirm. And do you think that temporal constraints should be added? And if yes, do you anticipate some issues like temporal correlations and so on? So in this case, we do actually PV power curtailment. So temporal constraints is not that necessary like if you were using a battery or some flexible device like heat pump and so on to do so like demand response to change or to act on the voltage. Of course, if you want to use other means than the PV power curtailment, if you want to use battery, of course we need to consider temporal constraints, and this has to be further investigated. So I cannot tell you exactly what should be the issues, but it has to be taken into account if you use devices where the temporal constraints is important.
Okay, thank you very much. Sorry for the other question cannot be answered here. You can of course ask them directly to Thierry through his email that you can find in his paper.